Alrighty, let's get started. So welcome to part one of our two-part webinar series, FEA modeling from start to finish. My name is Ashan John. I'm the marketing specialist here at Structural Design Analysis. So in this webinar, we're going to be covering the pre-processing and preparing our model for analysis. And we're presenting today is Dr. David Cross. He received his bachelor's, master's, and doctorate degree in aerospace engineering from Virginia Tech. And during his time with SDA, he's worked on developing static ground tests for UAV and also worked on the NASA Orion composite crew module. So without further ado, I'll let David go ahead and get started.
Thank you very much. Thank you everyone for joining us today. As Ashwin stated, today's webinar is FEA modeling from start to finish. So two primary objectives we have to communicate and convey and demonstrate to you in today's webinar is one, it being just a very introductory level demonstration of FEA modeling, what the process looks like and what's involved going from geometry to meshing to applying loads and boundary conditions. And then a second objective for those of you who may be already familiar with FEA, demonstrating the software that we'll be using today is Femap. And so hopefully you'll learn some about Femap, whether you've never seen Femap before or whether you're a new or somewhat experienced user of Femap. Hopefully you can take away something and learn something about the software. So those are the goals and what we hope to communicate today. So the basic agenda is we're going to go from start to finish. We're going to analyze a support bracket that's mounted to the exterior of a pressure vessel, and I'll show you that in a second. And then we're basically going to create a breakout of this model so that we don't have the entire pressure vessel, but just a portion of it. And then we'll start with geometry of our support brackets, and we're going to mid-surface them and mesh them, connect it up to the model, apply loads and boundary conditions, and you'll learn how to apply and force displacements. And then we're also going to use a data surface to help us automate and create a number of load set combinations. And then we'll set up our linear static analysis set. So we're trying to cover every step on the surface level, and what you'll find in these PowerPoint slides is we point you and direct you to other webinars that we've done on specific topics that go a little deeper into more detail on specific topics. So hopefully you can follow up with some of those if there's an area of interest to you. So this is what our structure looks like. You can see this orthogrid panel is a section of the pressure vessel. And then we've got this box or subcomponent mounted to the exterior, and it's connected up to the ribs of the orthogrid panel. And so that's what we'll mesh and edit today. So here's our starting model in Femap, and you can see the pressure vessel has basically already been meshed. So let's say this is an existing FEM that's already come out and is working, and now we need to analyze this subcomponent that's mounted to the exterior. So you can see we've got a box that's connected to this brown adapter plate by 4 bolts, and then the plate connects to our orthogrid panel with 2 bolts here going directly into nodes of the orthogrid panel. And then there are these 4 green brackets which are actually bonded to the ribs of the orthogrid panel. Now, the reason we're deciding to use a breakout model here is because the entire FEM of the pressure vessel, maybe many hundreds of thousands of nodes and elements. So it's very large. And to properly analyze this subcomponent and the brackets that support it, we need to analyze a number of inertial load cases where this thing is accelerated in any number of directions in the X, Y, Z directions and combinations of positive and negative accelerations. And so that can mean a lot of load cases. So then if we're applying a lot of load cases to this larger FEM, it becomes computationally expensive. So what we want to do is create a breakout model, a smaller model, where we can just carve out a section of the orthogrid panel. But in order to simulate the internal pressure, what we'll do is we'll enforce displacements that come from an existing result set where the internal pressure was analyzed. So we enforce displacements around the edge of the orthogrid panel and apply pressure cards to the interior skin of the orthogrid panel. And then on the smaller model, we can apply our inertial loads. So the first step I want to do is we're going to represent this box with a mass element. And so before I create that mass element, I want to create a group, and I'm just going to call it brackets. And I'm going to set automatic add. So what this will do is any entities that I create throughout the process will automatically go into that group. So the new entities we create, we can isolate and look at them aside from all of the rest of the orthogrid panel and things of that nature. So I'm going to go to Tools, Mass Properties, Solid Properties, and then I'm just going to select my box. And it asks me, okay, to create a representative node and mass element. I'm going to say yes. And then down here, instead of plugging in a density, I'm just going to say 0 node only. And so now if we drop down geometry, if I turn the box off and I turn on my nodes, I can see it placed a node right here at the center of gravity of this box, or the assumed center of gravity based on the geometry. And now I can define a mass element there. So I go model element, I'll select type, mass, and we select the node, and then we need to create a mass property. So if I click this button, it allows me to define a new property, and we're going to call this box mass. And the mass of this box is 1 pound, but our model is in slinches, so I need to multiply by gravity, 386.09. So now I've got my property defined, I've got my node selected, and there's my mass element. Okay, and so a little later we're going to connect that up to the adapter plate once we have it meshed. So the next step I want to do is create some mid-surfaces of these brackets that I can then mesh with shell elements. So what I want to do is I'm going to turn my elements and nodes off for a little bit. And then I'm going to use the Draw and Erase toolbox. So I'm going to select solids, and what this allows me to do, I'm going to select all, and then I'm going to remove from the selection the solids that I don't want to erase, right? The ones that I want to still see. So this is going to let me get rid of all the nuts and bolts here and washers. Simple as that. And now to mid-surface, I can go to Geometry, Mid-Surface, and for the brown one, I'm going to use this method called Single and Solid, right? And what this does is I just need to select the bottom surface of the plate, and then we'll select the top surface. Right? And you maybe could see some curves pop in there. So if I turn off round plate, you can see now I have a mid-surface. And so in a little bit, we'll mesh that with shell elements. But first, let's mid-surface these other bonded brackets. So if I say I'm going to turn off, you can also see on this model tree under geometry, when I created that mid-surface, it just put it here, number 29 mid-plane surface. So I'm going to turn that off momentarily. And then I'm going to go back to mid-surface. This time, I'm going to use automatic. And I'm going to do all of them at once. And it's asking me to select a target thickness. And so if I just hit the measure button, it asks me to measure, and I'll right click, I'll say snap to point. So measure from this point to this point, and you can see it's about 0.06 inches thick. And here I'm going to say combine mid-surfaces and combine tangent surfaces. So the combined tangent surfaces is the important one because as it mid-surfaces, it'll create a surface here and then a different surface through the fillet, and then on this angled edge, and then through this fillet around, and then the top, and it'll stitch them all together so that it's one single solid. And now what we can do is we can just highlight these mid-surfaces, say show selected only. I'm going to go ahead and cancel out my draw erase toolbar. And now you can see we've got mid-surfaces. If I turn elements back on, we've got mid-surfaces of our geometry. So at this point, I'm going to go ahead and mesh. And what you'll see in a little bit is that even after we mesh, we can still edit the geometry. So we don't have to finish completely editing our geometry. For instance, you can remove holes or remove fillets and rounds or change the size of fillets and rounds. So we'll see that after we mesh these. So I'm going to actually turn that off, and now I'm just going to get rid of the orthogrid panel. So I'm going to say show active group. And now to mesh these bonded brackets, I'm going to select mesh control size on surface. And I'll just select all of these surfaces. And I'm going to set the mesh size to 0.05, and we'll see if we like that size. So you can see once I did that, it drops or generates mesh seeds along the edges of these curves. And that looks about satisfactory to me. I think that's going to be a good mesh size. And so now to mesh it, we say mesh geometry surface. Again, we'll select all of our surfaces here. And again, similar to the mass element, it's asking us to define a property to mesh with. And so what's automatically filled in here, I think, is a property belonging to the orthogrid panel. We want to create a new property. Okay. And what you'll see is this says plate element type. And these bonded brackets are actually composite material. So we want to change the type to laminate. And you can see the form changes here, and it's asking for us to define a layup, which we don't currently have. So we can click this button to define a new layup. Now, in order to define a layup, we need a material for our plies. So we'll select a new material, and here I can define a 2D orthotropic material. In this instance, I'm going to select a load, and I'm just going to load this glass material that's already existing. And you can see it fills in the info. Okay, and then each ply, we're going to have 6 plies that are 0.01 inches thick each, and we'll say the first ply is a 45-degree angle, and then we'll have a 0 angle ply, a 90, and then we'll make it symmetric, so we'll say 90, 0, 45. So now the layup's been defined, and we can give it a title in a minute. I forgot to give it a title. And then we can set a bond shear allowable here in terms of the strain, so I'll just say 6,000. You can select a failure theory. So this comes into play in the post-processing. When you see the results, what Femap will do is taking the stress and strain results from Nastran, it'll calculate a failure index based on whatever failure theory you have selected over here. Okay, so now that our laminate property is fully defined with layup and material, then we have the option to use more meshing options, whether we have a mapped mesh or a free mesh. And those are things I'm not going to go into detail on. We'll just use the defaults. Say OK. And if I turn off surfaces, now we can just see our mesh, and it looks pretty good. And at this point, you can, as you'll see when we mesh the other bracket, you can have the ability to go back and update and change the sizing, or if you see elements that you don't like, you can control them. And we'll do that in a second. So now on a mesh, the main adapter plate here, and this is a metal plate. So we'll do the same thing. We'll say mesh control, size on surface. I'm going to make these elements a little bigger, so I'll make them 0.075 inches. Also, a lot of times like to use this min elements on edge. So if you have like a small round, it may decide to put one large element here. If I say 2, that'll force it, no matter how small, even if a curve or an edge is smaller than the element size I chose, it'll still force 2 elements to be in there. So that's something I use a lot. And now we can mesh this surface. And again, similar thing, it wants us to define, to select a property. And we're going to define a new property. And this one isn't a laminate. This is actually an aluminum. So we can change the type back to plate. And then we set the thickness. It's an 1/8 inch thick. We can call it adapter plate. Another thing so that we can differentiate it easily from the bonded brackets is we can change the color. So I'll make it purple. And then we need to define a material. So again, it comes in as orthotropic since that's the last material defined. So I'm going to switch it to isotropic. And then I'm just going to load a material that comes with the installation. So I'll just load this aluminum 7050. And now with our property defined, we can go ahead and mesh. And so now that we have our mesh defined, we can look at it and we can do some things to clean this up a little bit and make it a little neater. So if you go down here, this is called the meshing toolbox. What I'm going to use is the geometry editing. And I'm going to use this washer option with the washer factor of 1. And then I'm going to select these curves, and you can see it puts in a nice structured mesh around the circle, right? And then I can also do something like pad, and I can put a pad around all of these other holes. Now I can go a step further and I can adjust the sizing. So for instance, some of these elements don't look great to me, and I'd like it to be a little more uniform. So what we can do is go to mesh sizing, say set to, and if I highlight over this curve, I can see I've got 8 elements around this curve. If I look down here in entity info, as I hover over this, so this is 8 and this is 14. And so what I can do is say, okay, I like the size of those 14 elements, so let me update to 14, and I've got this select button still selected. Right, and I can update, and now I've got a nice structured mesh around this hole and around the outside there. And I can do the same thing to this hole, and then this one's a little bit different. What I can do here, so down in entity info, it's telling me I have 10 and 11, but this is in a full circle, so I think 8 ought to do it. Yeah, and then that way I don't have any bad trapezoids or triangular elements in there. Right? So these options, this meshing toolbox gives you a lot of live meshing control, a lot of flexibility to really drive the mesh the direction you want and make it, customize it to your liking. So one thing, I may not like the aspect ratio of these, so I may update the sizing to 3 on this edge. So if I select 3, it recognizes that this is a pad, and it goes ahead and updates the mesh in the whole pad, which is nice. Right? And so I can do that for all of these. So those are just some of the things you can do in the meshing toolbox. There's also things like feature removal. So now I can remove a curve, like say there's no need for this. It's not going to be critical to my mesh, so I can remove those rounds. Just keeps the mesh a little more rectangular. So a lot of different options there. Another one that I use a lot is point to edge. And so if I select this point and then this edge, I'll draw a line, and then I get a nice structured mesh. Right? You can adjust the sizing. 6. So you can see what kind of capability that meshing toolbox gives you. And we have other webinars we've done in the past that go into more detail on those. So check those out if you're interested. And now at this point, if we go back to our groups and right-click and say Show Full Model, okay, now we can see where we are here, and we can see that it's time to maybe start connecting these up, building the connections with rigid elements and C-bush elements to represent our bolted connections. And so to do that, we can say model elements, and I'll start by building rigid elements, and these are going to be RBU2s, and we're going to connect the mass for the box up to the adapter plate. So I'm going to say new node at center, and then if I select nodes, I come down here and I say method on curve, and then we select the curves around the hole. You can see it selects the nodes on those curves and drops in a rigid element. And so we can repeat this a few more times. And the last one here. And now I do have an option where if I wanted to be able to pull loads from these connections, I can put C-bushes in there. That's likely what you would want to do. In this case, just for time and simplicity, I'm just going to connect another rigid directly to it. And this is going to be an RBE3 for the mass element to properly distribute the load to the adapter plate. And this time we don't want a new node at center. We want to specify the node as that of the mass element. And then selecting our independent nodes with the RBE3 to be just the center of these rigid elements. There you go. So the next step would be to build our bolted connections here between the adapter plate and the bonded brackets. And in order to do that, building these types of connections a lot, instead of going through the usual menu and defining one rigid element, then another rigid element, and then the C-bush, I wrote a custom API. And this is something that as you begin to learn Femap and use it a lot, you'll notice there are lots of operations you do that become repetitive, and in order to increase your speed and efficiency in using the software, you can learn to write these APIs to speed up those operations. And so this one I called C-bush connections. And what this API does is it just walks you through some of the typical steps that we would use to build this type of connection, but just in a cleaner, more efficient way. And so here it's asking me to select the nodes for the first rigid spider. So that'll be the nodes on the adapter plate. And then it wants me to select the nodes for the second rigid spider, so on the other structure, which will be on the bonded bracket. So say method on curve. So I can select this, and then the clip sort of connects it to both, that clip that was there. And then it's going to automatically create a C-bush element at the center. And so I can either locate it or let it just put it directly on the center. And so now you can see it automatically generated the first rigid and the second rigid, and then put a C-bush element directly there. So that's a really nice capability, because now I can just cycle through and I can do these other ones. And in fact, while I build these few other connections, I think Ashwin's going to ask another poll question. And so maybe take the time to answer that while I just walk through those same steps of building these other connections, and then we'll continue on to the next.
Right. So while David's doing that, just want to answer this poll question. So which of the following solutions do you run? Just give it a few more seconds, and then David, whenever you're ready, I can close it out and send it back to you.
Okay, great. Yeah, I'm on the last one now. So.
All right, I'll go ahead and close it out and send it back to you.
Okay, thanks. And So now I use that API to go ahead and quickly build these 4 connections. The one thing that API does is just throw a random CBush property in there. So we need to make sure that our CBush property is properly defined. And so in order to do that, the first thing I want to do is say update elements property ID, because it created a couple different properties here. Right, so with those CBushes selected, I'm just going to make sure they're all the same property. And then I'm going to edit that property. And I like to typically actually set up my CBushes so that the Z direction is the axial, is the bolt axis. And so therefore I'm going to release the 6th degree of freedom for the bolted axis rotation. And then I'm actually, you'll see here, I like to define the orientation system. You can either define it on the property card, or you can define it on the element card. So I'm going to uncheck that and show you where that is on the element card. But first, we want to define the coordinate system. And so in order to do that, you go to Model Coordinate System, and I'm going to use the XY locate method. And we'll just call this coordinate system bolt CBushes. And so the first step is it just asks me to select the origin. And so I'm just going to select this node here. And then the x-axis, I can say, runs along the rib. Right. Well, actually, let me repeat that. XY locate. Let me choose a different location. So let me choose this node. And then we'll say that the x-axis runs along the rib, and then in the xy plane. And so that you can see Z is going to be the bolt axis downward. And now I can update those elements by property. And I can, on the element card, so this is where the definition of the CBush, you can see it's pointing to my CBush property in node 1 and node 2, and I can update the orientation coordinate system to the one I just created, which is ID3. Now, in order to fully model this, I would have to create a few more rigid connections. You can see this one over here, and this one over here that go directly down in the orthogrid panel, and then also the connections between the bonded brackets and the orthogrid ribs. But just to spare us a little bit of time of just going through those repeated steps of creating rigid elements and CBushes, I'm going to move on to creating the boundary conditions and the loads. So what we'll first do is define some constraints. So I'm going to minimize geometry and turn all my geometry off. So if I drop down model, in the model tree, you can see things here like elements, materials, properties, layups, loads, and constraints. So I right click and say new constraint, and I'm going to call this fixed edges. Now these constraints are necessary because we're using enforced displacements. And enforced displacements, basically Nastran, when you run Nastran, it views that as a constraint. So in Femap, we have to define the constraint and then the load as an enforced displacement. So the first step of that is defining the nodal constraint. And so I'm going to select all the nodes along the edge, my bracket. And then I can highlight because I think I missed a few, right? I got one too many here. So that highlight feature is really useful and nice. Use it all the time. So it looks like we have them all. So select OK, and then we can define the constraint as fixed. And this is important because my enforced displacement, I'm going to enforce a TX, TY, TZ, an RX, an RY, and an RZ. Since I'm doing all 6, I need to use specified as a fixed constraint. Okay. And now we can define a load case, and we'll call this the enforced displacements help us simulate the pressure. So I'll call it pressure. But now in order to define this, what we're actually going to do is utilize a results file. So this results file was a file that I ran previous to the webinar on the entire pressure vessel. Okay, and so this results file contains, for that internal pressure case, the displacements and rotations of the nodes that we want to enforce. So all I have to do is drag and drop this OP2, my Femap window, and you can see now I have it in here as a result set. Right. And if I can actually view that by specifying displacement. And you can see, obviously, these brackets weren't in that internal pressure run, so they don't have displacements or results. But you can see how the orthogrid panel deforms due to the internal pressure. So now, in order to create those enforced displacements, with our load set active, meaning it's I've double-clicked it and activated it, so that's why it's bold and blue. And with our output set active, we can say model load from output. And then the type of load, nodal load, we're enforcing is a displacement. And then it is not on all the nodes, so we do not want to select all. So we want to uncheck that box. And then we press OK. And then it asks us to specify from the output set which output vectors are we enforcing in the 1 through 6 degrees of freedom. So obviously our X vector, we want to be T1 translation, and then T2, and then T3, and then our rotations, which are 6, and then I can just type 7 and 8. So say OK, and now it wants me to select the nodes, and this is the part I actually forgot to do. So this is a good example of what happens sometimes in Femap. So I have to hit cancel, and the easiest way to reselect those nodes, in my opinion, is to right-click on the constraint definition, say Edit Where Applied. I've got all those nodes, so now I want to say Pick Copy as List. So now I've got those nodal IDs on my clipboard. So now I want to create the load. So model load from output, so we can repeat those steps quickly. I can say 2, 3, 4, 6, 7, 8 to get my T1 through T3 and R1 through R3. And now I can just Control-V and paste in those nodal IDs, highlight to make sure. Okay. So now these buttons up here just turn on and off the visibility of our constraints and our enforced displacements. Okay. So the next step for the pressure is we also have to define pressure forces on the inside of our orthogrid panel skin. So if I right-click on load definition, I can add an elemental. Okay, so elemental, and I'm just going to say select all. And then the pressure value here is 12.45 psi's. And then here it wants me to pick the faces, and so I can just pick one orthogrid skin face. And then this is an angle tolerance, so it's only going to add to my selection elements that have a normal vector within that angle tolerance. And so by selecting more, it adds into the selection. I highlight, and I can see it's just the skin. So if I press OK and show the loads, we can see I've got pressures defined on the bottoms of the skin there. And now what I want to do is create all of our inertial loads. And these I'm just going to sort of do on the fly, but show you how to use the data surface editor to create load set combinations. So we'll call this load case AX for acceleration in the X direction. And so let's say it's a body load. the active, and let's say it's 20 Gs, and again our model's in Cylindrical, so we need to multiply by gravity. And then what I'm going to do is I'm basically just going to create an AX, an AY, an AZ, and then I'm going to create a second AX, AY, and AZ. And so what I can do is I'm going to edit the title here. And then so it's 20 Gs in the X, only 15 Gs in the Y, this instance. And then AZ is going to be 25 Gs in the Z direction. And then I want a second set. So what I'm going to use the data surface editor for is combine these in all plus and negative combinations. AY2 and AZ2. So AX2 is going to be 30 Gs in the X. Right. And then AY2 is only going to be 10 Gs in the Y direction. Oops. And AZ is only 8 Gs in the Z direction. So now that I've got those basic loads defined, we can open our data surface editor. If I drop this down, these are the different types of data surfaces you can create. And we'll create the load set combination data surface. And so the number of rows is basically how many load combinations we're going to make. So in this simple case, what I'm going to do is combine AX, AY, and AZ. So there's 8, plus minus, plus minus, plus minus. So there's 8 combinations and then 8 more for the second set. So 16 total loads. And then it's asking me which existing load sets do I want to combine. So I'm going to utilize all of them. And so here I can give specific set IDs and titles if I want. And then you can basically plug in this table the scale factors you want to apply it. So the pressure is going to be applied to all load cases. And then AX is going to be positive, or it's going to be negative, right? And AY, I'm going to have alternate every 2, and then AZ, I'll alternate every 1, right? And then for the second set, I can just paste that in here. So now once I have all the scale factors defined, all I have to do is right-click and say create combined sets. And you can see it populated all of my load sets here and sort of shows me the scale factors in which load cases were combined. And so that's just one way to do it. A lot of times in-house here we have APIs to help us create these sets when we have hundreds of them. But I thought that was a useful tool to show the data surface editor. And now we can define our analysis set. So we say manage, new, and this is just going to be a linear static. So internal pressure and inertial loads. And for this basic linear static analysis, the majority of the defaults are acceptable. And so I'm just going to click through and then actually not going to define the constraints or loads here because we're going to define multiples, and we'll do that in a second. And then the output, I can just leave this as full model. We'll leave corner results on and post-process only. So to apply all my different load cases, I can select multi-set. And then I want to turn these general load cases off and then only include all of our load case combinations that we created. And then since I'm having the same constraints on all of them, actually can turn that off, and under master I can specify the constraints as a master constraint set that get applied to all load cases. So that gives you the ability to specify different constraints for different load cases if you want. In our case, we have the same ones in all of them. And so that's our analysis is fully set up and ready to run. I'm not going to run it today because I didn't want to bore you by building too many rigid C-bush connections, so I don't have it fully connected up yet. So I'm going to go back to our PowerPoint slides and just sort of review what we did and the steps we made. So we have a webinar that Ryan, an engineer at SDA, did on developing breakout models in Femap. So that might be useful if you think that's something you haven't done before but might want to do. And then we created the mid-surfaces of our geometry. We meshed those mid-surfaces, and then we edited the mesh some on the fly. And so we have additional webinars which go through in more detail the geometry preparation and manipulating that meshing toolbox. And I did use an API just to kind of show you, the types of things that APIs can be used for. But we have a great introduction webinar on API programming if that's something you're interested in. And then I used the data surface editor to create all those load set combinations. And there's lots of different ways you can define loads and do load spreading for when you have gradient pressure loads and things of that nature. So we've also got a webinar on that. So a lot of different topics there that you can dive into if you're interested. And then creating just a linear static analysis set. This is another good general webinar that goes through the FEA process that we've done in the past. And so part 2 of this webinar will take place on January 10th. And what we'll do in that webinar is finish this one up where it'll be fully connected up, and we'll run the analysis and then check through all the different results. So we'll look at contour stress plots, we'll look at C-bush forces, how to utilize the data table to extract results information, which you can then put in Excel and manipulate or pull into other tools that you might have, and enveloping results so that you can look at your max and min stresses, things of that nature. And so I think at this point, Ashwin has some announcements to make, maybe tell you a little bit about our company, and we'll take a look at some of these questions that you're asking and answer some of those.
Yeah, so I'm going to attempt to launch the poll while we switch over screens. And David, while I'm talking about the upcoming events, you can just look over the questions. Go ahead and submit your questions to David through the question panel in the GoToWebinar panel.
Yes, so someone asked a little bit about, is the C-bush connector available to the viewers? And yes, it is. So you can view C-bushes and all the details about it right there in the Femap window. And I'm guessing you saw that once I created the C-bushes here. So you can see the C-bush connection in the viewer. And then another question was, how would we represent this bond? There's a lot of different ways to do it, and it depends on the detail of the bond margins you want to be able to write, or the bond analysis you want to be able to do. The simplest and most basic way to do it, if you just want to get sort of like a global bond line force, almost just knowing how much load is going to be going into that bond, then you can just do a single C-bush connection. And so what I actually would have done in this case is create an RBE2 on the center that connects to orthogrid rib, and then that RBE2 would actually spider to a C-bush for this bond line and a C-bush for the other bond line. And then going from the other sides of the C-bushes, I would use an RBE3 to spread, to spider out to all the nodes on the surface representing the bond area. And so that's a very simplistic way of doing it, but it does get you get you those forces out in a simple way, which you could then do some very simple bond margin calculations with.
Great. Yeah, so I'm just going to go over a few slides, and if you have further questions for David, please just submit them in the questions panel. So as David mentioned, the second part of this webinar series will be covering post-processing, and that will be on Tuesday, January 10th at 2 p.m. Eastern. So if you're registered for this webinar, you're automatically signed up for that webinar. But if you like this and you think that your colleagues would be interested, they can visit this link right here, Structures.Aero/FEA modeling start finish, and they can register for it as well. So about structural design analysis, we are a group of 14 stress engineers who work on projects for companies such as Aurora Flight Sciences, NASA, and Lockheed Martin, as well as companies like Vanilla Aircraft. And we've done work on the NASA Orion Composite Crew Module, the Aerosun, and other cool projects. And to do this, our stress work, we use Siemens PLM software as well as Collier Research software HyperSizer. And you can learn more about any of these software products on our website or by contacting our sales manager, Marty Civic, who I'll get to his information in just a second. And we'd like to invite everyone here to this free event at Piper Aircraft in Vero Beach, Florida. At this event, you'll be getting a tour of Piper's facilities and get to see the M600, which we helped work on. There will also be presentations on how Femap was used to create the Piper M600 wing fuselage. And the Femap development team will also be there, so they will be talking about what's new in Femap, as well as having a roundtable discussion where you'll be able to request features, or they'll address your complaints. And you can find more information about that at Structures.Aero/Femap Symposium. And lastly, like I mentioned, if you have any questions about pricing or would like to see a demo, you can contact our sales manager, Marty Civic. Or if you have questions about this webinar, you can contact David Cross. And right before I pass it back to you, David, I also wanted to show there's a few resources on our website. So on our website, the software that we discussed, you can find out more information about that by going under our softwares tab. And you can also view the webinars that David had mentioned throughout. We have it under our resources tab under webinars. You can go through and filter through all the webinars that we have done. There's more than 12 hours worth of free content here. So we would love for you to be able to take advantage of that resource. So David, yeah, I can, if anyone had any other questions, you can go ahead and answer that now.
Yeah, there was just one question. Someone asked if the API that I used to connect up the ridges and sea bushes if that was available to the users, or something we could make available to the users. And I think it certainly is. I would want to clean it up and comment it a bit. But if you're interested in that, you can go ahead and email me requesting it, and I'll send you a copy of that API for sure.
Right,
but yeah, there were no other questions. Thank you everyone for listening and dialing in. And like Ashwin said, if you have more questions about this webinar or otherwise, please don't hesitate to contact me. Thank you.
Great. Thank you everyone. Have a nice day.